Okay, welcome to the session on material models in 3DEC. This is Jim Hazard, the 3DEC product manager here at ITASCA. So far, the example that we've seen was made with rigid blocks, meaning that they did not have zones and they were not deformable. Most of the time, people using 3DEC are creating deformable blocks, meaning that they have zones inside of them. They can deform and they can even fail depending on the constitutive model. Rigid block analyses are useful if you are, for example, close to the surface where there's low stress, or most of the important mechanisms that are occurring are on the joints and you don't really care about deformation of the blocks. Again, in most cases, people will make the blocks deformable. This is important, especially if you expect there to be failure or plasticity in between the joints, and this particular failure mechanism is important in your model. So when you zone the model, you need to assign a constitutive model. This is the same as any continuum program. What you have is essentially small continuum models inside of each block. A constitutive model is just a mathematical simplification of complex material behavior, from the beginning of load up to and beyond failure. Even though behavior mechanisms may be different, many materials behave similarly at a macroscopic observed level. So the point of constitutive models is that, we don't necessarily want to model all of the micromechanics of everything that's happening, down to the grain scale, for example. And we will have an equivalent continuum with some behavior that will represent the microscopic behavior at the macroscopic level. So a constitutive model describes the stress-strain behavior in response to applied loads. So this is the typical graph you would see where you have stress on the y-axis and strain on the x-axis. Often the material will start out behaving elastically, so there's a linear relationship between stress and strain. And then there will be some sort of failure or other behavior occurring when you reach some stress state. And then what happens at that point is really specific to the constitutive model. Often these things are interestingly nonlinear, and all kinds of interesting things can happen at or beyond the failure point, depending again on the constitutive model and the properties that you set. So in the rock mechanics world, and to some extent soil mechanics, this is generally the range of behaviors that you would expect. So often these models start out to be linearly elastic, and then they have some sort of strength. And when that strength is reached, they either become perfectly plastic, so they will continue to deform at a constant state of stress. This is more common in soils. In rocks, especially, competent, bulky rocks, you might see something that's much more brittle. So perfectly brittle would be an instantaneous loss in strength. More commonly, you will have some sort of softening, so the loss in strength is not instantaneous. And occasionally, we'll even see something that has plastic hardening. So just as an example where these different situations might occur, again, imagine you had a massive, fairly competent rock without maybe a lot of joints or alteration or something like that, a relatively deep tunnel. You might expect to see fairly brittle behavior in this case, and a stress strain curve that looks like the one in the top left. And then what you would see around your tunnel in this case would be some sort of spalling, probably. The bottom left is maybe a case where there's some more jointing or not quite as competent rock. You might see more of a strain softening type of behavior in that case. And you'll see potentially some movement on joints and things like that, rather than this spalling. And then on the top right, this might be a soil model or a heavily weathered rock or something like that. And you might get more of a plastic type behavior where there's deformation and failure, not necessarily on joints, but just sort of overall throughout the rock mass or soil. There are many, many constitutive models inside of 3DEC. This is not all of them. This is the ones that you will probably likely use. I'm assuming for this presentation that you're probably modeling rock. If you're a soil mechanics person, likely you are doing FLAC 3D or some other continuum program. 3DEC, as you probably know, is mostly used for modeling rock because of its ability to consider joints and discontinuities and things like that that are common in rock. And so the commonly used constitutive models when you're simulating rock systems are highlighted here in bold. So elastic is the simplest possible thing you could come up with. Mohr, the next simplest, and is very commonly used. Does not require a lot of parameters and is very well understood by many people. I'll jump forward to the Hoek-Brown model. Is essentially a curved failure surface, which I'll show in a minute. Again, very commonly used in rock mechanics. Strain hardening, softening Mohr-Coulomb. So the basic Mohr-Coulomb model assumes perfectly plastic. It is certainly possible to have a softening behavior after failure. That would be the softening Mohr-Coulomb model. It's possible to consider softening in Hoek-Brown as well. That's just built into the same model. And then one constitutive model, which is maybe less well known, but it's still quite useful, is the ubiquitous joint model to simulate a whole bunch of joints or create a model that acts as if there was a whole bunch of joints there without actually having to simulate them. And I'll show that a bit more detail in a minute. There are some other models here that you might be interested in. I won't go into detail about them. There are also several models related to creep. So creep is time-dependent deformation, where you reach a certain stress state, you're not changing the stress, or at least you're not changing the boundary conditions, and yet the model is still deforming. And this would be a creep model, and the rate of deformation, or sorry, the amount of deformation depends on the time and also the level of stress. Also not going to talk about these models. It is also possible to create your own constitutive model. This is fairly common in soil mechanics, where people have different interesting behaviors for different specific soils. In the rock mechanics world, this is less common. I don't see this a lot in 3DEC. However, it's also possible to create your own constitutive model for the joints, and I'll talk about that in a future session. So I won't go into detail here about how to create your own model, just to let you know that it is possible, and it is described in the documentation. Okay, so how do you choose what type of model you are going to use, or which constitutive model you want to use? Does it describe the physical behavior occurring? Can it be implemented? Obviously. Is it sufficiently accurate? The advice here is to start with the simplest constitutive model first. So almost always it's a good idea to try running a model with the elastic model. You know that it will solve, it won't fail, it will come to equilibrium, assuming that you've set up your boundary conditions correctly. It's a good test that everything's working correctly. Then you start adding complexity to it. Often the next most complicated model would be Mohr-Coulomb, where you give a cohesion and a friction, and then you might get more complicated from there. So as advice, everything should be made as simple as possible, but not simpler. I'm not sure this is actually Albert Einstein, but it's often attributed to him. For example, if you were trying to run a factor of safety calculation for a slope, it makes no sense to run it elastically because, of course, it doesn't fail. The simplest possible case here would be Mohr-Coulomb. If that's all you're trying to find out, a factor of safety, then that would be sufficient. So if you choose a constitutive model, obviously there will be some parameters associated with that. The next challenge is figuring out what those parameters are. Often you might have lab data or even sometimes field data, some relationship between stress and strain or something like that. Often this data will be noisy, inconsistent, variable. The challenge here is to just pick the parameters that will closely match the data, or at least as close as reasonably possible, and not go crazy trying to match every single bend in the curve or all the variability and so on. We know that geological materials are variable. We know that we do not have the ability to really nail down the exact behavior of these things. You try to catch the important components with a constitutive model and not worry too much about all the zigzags here. And just one quick mention about the effect of water. There's a whole other session about water in 3DEC, but it is important to mention here while we're talking about constitutive models that when 3DEC is checking to see if a material has failed, so it's checking the stress state versus the strength, it uses the effective stress state. So if there's poor pressure in the model, it will use the effective stress state. It essentially reduces the stress, and it uses that to check if the material fails or not. So poor pressure will have an effect on the potential failure of models in 3DEC. Okay, so that's basically the background. Obviously, you need to implement this in 3DEC. You can do it with commands. It's also possible to do it with fish. You can change the constitutive model and the properties using fish if you want to. This is useful if you want to loop through all the zones and give some distribution of properties or something like that, you know, depending on a location or something like that. So the ability to set these things with the scripting is totally useful. If you're doing strain softening, either with Mohr-Coulomb or with Hoek-Brown, you will need to use tables, and the tables describe the relationship between the amount of softening and the amount of plastic strain. And I'll show that in a minute. So the syntax looks like this. The first thing you have to do is create the zones. So you generate the zones with some command that looks like this: block zone generate edge length. Once you have zones, you assign them a constitutive model. So in this case, in bold is shown how to assign a Mohr-Coulomb constitutive model to all the zones. As I showed earlier, you can use a range to assign different constitutive models to different parts of the model. In this case, it defaults to the whole model. Once you have a constitutive model, then you can assign the properties. Note that you can't assign the properties before the constitutive model because it doesn't know what properties exist. So here's just how to do that. Here's the syntax: block zone property, and you give the name of the property and a value. Note again that we are not specifying any units in 3DEC. And this was talked about before. You just have to be careful to be consistent. And this chart is from the manual in the underpinning section. And again, if you just go down one of these columns and make sure that you're consistent with your units, everything will work out. Most of the examples in the manual are down the left-hand side here, using meters and pascals. In the rock mechanics world, often people will like to use megapascals, so you don't have such large numbers, and that's fine. The length unit is still meters. Gravity is still meters per second squared. You just have to be careful with your density and divide your density by 1 million. And again, often in the United States, you will see imperial units, in which case the length would be feet and the stress is pounds per square foot. And just a quick note about sign conventions. We don't need to talk about all of this, except to note the sentence in bold at the bottom. Compression is negative. So compressive stresses are negative and compressive strains are negative. This is different from a lot of other geomechanics types codes, but similar to mechanical engineering type problems where tension is positive. You just need to be a little bit careful here because sigma 1, what we refer to as sigma 1, being the most compressive stress, will be the most negative. So it's actually the minimum stress, if that makes sense. So just be aware of that going forward. There's extensive documentation about all of these constitutive models. And I think there's probably at least one example for each one of these constitutive models just to show how to use it and how to set the properties and so on. Okay, so I'll just talk about a few of the constitutive models that you are most likely to use and just give a little bit of detail. The elastic model, and all the ones that I will talk about are based on the elastic model. So at a bare minimum, you need to give 2 elastic parameters. Usually in real life, you're specifying Young's modulus and Poisson's ratio. This is usually what you have. You will see a lot of the examples in the manual use bulk modulus and shear modulus. And this is because there are certain circumstances where Young's modulus and Poisson's ratio don't make sense. For example, something that's getting close to being water, where there's a very, very low shear modulus. However, in reality, that almost never happens. So it's generally safe to use Young's modulus and Poisson's ratio. If you need to convert between them, here's the equations. And that's it. So for elastic, all you need is Young's modulus and Poisson's ratio. That's it. The elastic models will never fail, of course. They will just deform happily and undeform happily along a straight line. If you want something to fail, probably the next most simplest one is the Mohr-Coulomb. And probably you are familiar with this already. With the Mohr-Coulomb model, you specify a cohesion and a friction angle. And what you have is a failure envelope. So if we are plotting shear stress in a zone versus normal stress in a zone, this red line is the failure envelope. So to the right of this line are permissible stress states. So you have low shear stress or high normal stress. To the left of this line, or left and above, are not permissible stress states. These stress states cannot exist in a Mohr-Coulomb model where you have high shear stress or low normal stress. And the dividing line is this red line. And the equation here is, again, a super simple straight line equation. Cohesion plus the normal stress times the tangent of the friction angle. So the cohesion is just the intercept. The friction angle is just the angle of this line. This is a very well-known model, and you guys are probably all familiar with this already. The only interesting wrinkle here is that in the world of rock mechanics, we often like to plot things as sigma 1 versus sigma 3 instead of shear versus normal. When you plot this as sigma 1 versus sigma 3, it's still a straight line, but the numbers here are a little bit different. So the intercept is now the unconfined compressive strength. So essentially the strength at 0 confinement. And you can actually calculate that from cohesion and friction. The slope of this line is some function of the friction angle and the cohesion. Again, you can see it over here in the equation on the right. One other thing to mention about Mohr-Coulomb is that as well as a cohesion and friction, you almost always specify a tension cutoff. If you do not specify a tension cutoff, it assumes that the tensile strength of the material is the x-intercept over here on the left. That is almost always stronger than the real rock. We know that the rocks are fairly weak in tension compared to compression. And so almost always you will want to specify some tension cutoff here so that you cannot have tension strength less than this particular value. Okay, that's all I'll say about Mohr-Coulomb. Moving up in complexity from that, we have this ubiquitous joint model. And what this is it allows you to simulate a rock that maybe has very closely spaced bedding or some sort of lamination or schistosity or something like that. You don't actually want to model all of these joints because it will make a very computationally intensive problem. But we can do some mathematical trickery here to make the zones behave as if there was a whole bunch of joints in there, a whole bunch of parallel joints in there. So the situation might look like this. We're not actually modeling the joints. We're just coming up with a constitutive model that behaves as if there were joints there. So you have this matrix material of Mohr-Coulomb, and then you have these sort of fictional joints. You specify an orientation, you specify a cohesion and a friction for the joints, as well as a cohesion and a friction for the background material. There's an example in the manual. This is FLAC 3D, but you can run the same thing in 3DEC. You can imagine an unconfined compression test on a cylinder. And depending on what angle you choose for those ubiquitous joints, you get different strengths. So if you say the ubiquitous joints are at an angle of 30 degrees, you get the minimum level of strength. And it varies from there. You know, if the joints are at an angle of 90 degrees, then you get the sort of background strength. Okay, so the next thing is strain hardening softening. This is basically just the Mohr-Coulomb model, but instead of being perfectly plastic, you can have the strength decreasing as it fails. And so what you have is a relationship between the plastic strain. So these graphs here, this E superscript PS is plastic strain. And then whatever property you want, you can vary with plastic strain. So in this case, we're showing cohesion and friction. Often there will be a reduction in cohesion with plastic strain, and often a reduction in friction with the plastic strain. And the way this is defined is with a table. So you give the peak level of cohesion and friction and tension, as I'm showing here with commands. You create tables. So these bottom two lines are creating a table with X, Y points in it, right? So X is the plastic strain, and Y is whatever the value is, friction or cohesion. So let's look at the friction one. So at 0 plastic strain, when it just starts to fail, the friction is 45 degrees. A little bit after that, 0.05 plastic strain, the friction is 42 degrees. At 0.1, the friction is 40. And then at 1, which is essentially infinity, it's still 40. So you've got a flat line at the end here. Same thing for cohesion. Once you define the table, you just say block zone property, and you tell it which table to use for friction and which table to use for cohesion. This example here is slightly more complicated than you would probably see in real life. In real life, we don't generally know the details of this curve to this extent. You would almost always just give 3 points: the starting point, the minimum point, and the infinity point. And that's basically a straight line relationship between the cohesion and the plastic strain, or the friction and the plastic strain. And actually, this is shown in the next plot. So here we've got on the left side elastic, perfectly plastic. So it loads up elastically, it fails, and it maintains the same strength. The friction is constant, the cohesion is constant. With strain softening, the first part of this curve is the same. It hits the peak strength, and then you get a gradual reduction in friction and cohesion. Look, this graph on the bottom here is upside down. Cohesion is greater going down. So there's actually a reduction in friction with plastic strain. And again, this is the straight line relationship that is the most commonly used. A reduction in cohesion with plastic strain, and what you end up with is the residual strength is quite a lot lower than the peak strength. And so this is thought to be the way that rocks mostly behave, with some sort of softening, rather than perfectly plastic, which is more common for soils. The last model I'll talk about is Hoek-Brown. Again, very common in rock mechanics. Assuming you're probably familiar with this, be aware that this is a semi-empirical model, so there are limits to when this is really usable. The recommendation is that, if you have a moderately jointed rock mass with 3 or more joint sets, then this is a useful model. If you have 1 or 2 joint sets, there's definitely anisotropy in the system, and this does not capture that. We're assuming here there's enough joints in the system that it basically behaves isotropically, the same in all directions. And again, we're assuming that it's not completely disintegrated, which would be a very low GSI, or super, competent, which would be a very high GSI. The point of this model is to try and simulate a jointed block or jointed rock material isotropically, with some moderate amount of joining. Probably you have seen this before. This is again the failure criterion plotted in sigma 1 versus sigma 3 space. Mohr-Coulomb might look like this with a dotted line, right? It's a straight line. Hoek-Brown is a curved line. It's basically a parabola on its side. The reason that people use this in rock mechanics is that because when you get up to these states on the right-hand side with very high confinement, the Mohr-Coulomb gives you a strength that is too high. We know that these high levels of confinement, rock is often not as strong as the Mohr-Coulomb line would suggest. And so we have a curved line instead, so that as the confinement increases, The strength still increases, but not as dramatically as it does for Mohr-Coulomb. So parameters that define that curve, sigma Ci, the uniaxial compressive strength of intact rock. So pretend you have a lab study on a relatively small piece of rock. This would give you the intact strength of that. And then there's an MB parameter, which is the degree of block interlocking, more or less, and an S parameter, the condition of interblock surfaces. And there's also this A parameter. Traditionally, this is 0.5. It's an exponent of 0.5, which basically gives you that parabola. It is also possible to change this A parameter. In reality, people generally do not know what these MB, S, and A parameters are. What they do know is usually GSI, geological strength index. And I'll show that on the next slide. But what you can do in 3DEC is just specify sigma Ci, which is usually known, GSI, which is usually known, and this damage parameter D, which I'll also talk about in a minute. And then these other parameters are automatically calculated. So MB, S, and A are calculated by 3DEC, and you don't need to worry about it. And here's the equations over here. If you're interested, it's also in the manual. So this is a very well-known chart that you've probably seen before, which tells you how to get the geological strength index. Again, be aware this is somewhat subjective. You know, you look at your rock and you make some call about how much jointing there is and what condition the joints are, and you pick a GSI off this thing. It is certainly not an exact science. Once you have the GSI, you can calculate those failure parameters, as in the previous slide. People also use this to calculate modulus. So here are some equations for calculating the Young's modulus of the rock mass. Look at the second one here. Often you will know the Young's modulus of the intact rock. So for example, you did a lab study on a small piece, you know that Young's modulus. But of course, in a rock mass that's full of joints, the Young's modulus will be less than that. So you can scale the intact modulus by some function of GSI and this damage parameter. And this again is empirical. This is come up with by fitting a bunch of curves to some actual data to come up with this. Similarly, there's an equation for Poisson's ratio based on GSI. This is also empirical and should be used with caution because there is much less data available to nail down this equation. People definitely use this, but it's really not super robust. As mentioned, there's this other parameter, the damage factor. This just allows you to scale the strength and the stiffness to account for the fact that there may be damage in the rock, usually due to blasting or possibly unloading, if it's like an open pit or something like that. So you can assume that, you know, far away from the surface, or maybe you did like a TBM tunnel or something like that, where there isn't a lot of damage on the surface, the D value is 0. That's the sort of default undamaged material. In the extreme case, maybe you're right next to where there's a big blast occurred, or there's some excavation that caused a significant change in the surface conditions. You might get up to a D of 1. That's the maximum value. So your D ranges from 0 for undamaged to 1 for totally damaged. In reality, you're probably in between here somewhere. Strain softening for Hoek-Brown is built in. So be aware that for Mohr-Coulomb, there are two separate models. There's Mohr-Coulomb, which is perfectly plastic, and there's strain softening, which is actually Mohr-Coulomb with strain softening. In Hoek-Brown, it's the same thing. You can run your Hoek-Brown perfectly plastic, or you can run the same Hoek-Brown model with strain softening by using tables, as I showed before. Be aware with strain softening that the behavior is somewhat mesh dependent. So one of the parameters you will recall is this critical strain, or the plastic strain over which you see this weakening. Strain, of course, is the change in length over length of an individual zone, and so the size of that zone will actually make a difference to the behavior of the system. And so probably what you want to do, the critical screening by the zone size, and this is built into the Hoek-Brown model. You can just set a property length calibration equals 1, and it will automatically scale things by the zone size. This is not built into Mohr-Coulomb strain softening, so you would need to do this by hand or with fish or something like that. All right, I'll just summarize, and then we'll just show a little example just so you can see how this actually works in a model. The summary, again, first, try to capture the key behavior and ignore the insignificant behavior. Do not use any constitutive model if you do not understand it. Certainly there are some very complicated constitutive models out there with many parameters. You can use these things, but often it's very tempting to just go and keep tweaking parameters until you get what you want. When in reality, it's better to try and understand the mechanics of what's happening here. Understand the Mohr-Coulomb model. Pretty much all the models that we use in rocks are based on the Mohr-Coulomb model. Not necessarily true in soils, but in rocks it certainly is. And it's easy to understand, and you should be very familiar with that. Okay, I have a relatively simple example here just to show you how you can assign constitutive models and properties and run a model. This is just a 10 meter by 10 meter cubed. It's meant to be like a section of a open pit bench. So imagine we had this extended into the plane and out of the plane. So it was actually longer than I'm showing here, and there's some symmetry. Imagine we were trying to simulate a bench and we wanted to see whether it's going to fail or not based on certain different rock material properties. So this has no joints in it. This section is all about zones and zone constitutive models. We can do that in 3DEC. We can make a purely continuum model, and that's what we're going to do right here. So you should have this example in your material that you downloaded. So I'll just show that where that is. So, okay, first thing you want to do is start 3DEC. All right, I'm going to make a new project. You could, again, I've given this to you. You could, in theory, just open the solution and follow along. But I will do it from scratch here and do some typing, and you can see how it looks. So I'm going to make a new project. I'm going to go to where the training material is, wherever you downloaded it. So I'm in training, 3DEC. There's a directory called material models. There's a directory called bench. And inside of that, there's a directory called solution. So that's where you can find the finished model. But let's instead make one from scratch. I'm going to call the project bench. And almost always when you make a new project, you need to start with a data file. So I go up to here and say new data file. We'll just call it bench. Here's my blank data file. As mentioned in the previous session, almost always you want to start with model new or model restore if you're following on from something else. What I just did there was I held down control and moved the mouse wheel to make the font a bit bigger. Okay. First thing to do is create a block. So this is the same thing we've seen before. Block, create, oops. Create, brick, and I give the minimum x coordinate, the maximum x coordinate, and by default, it will give the y and the z coordinates the same. So I'm going to assume this is in meters. Probably roughly the height of a bench in a relatively competent rock in an open pit mine. We'll see what happens. Now, the new part that we haven't seen yet. So what this does is it just creates a single block that is rigid. If you want that block to deform, we need to fill it with zones. So you need a command like this: block zone, generate edge length, and you give some number. Almost always in 3DEC, you are filling up your blocks with tetrahedral zones. Okay. So what this edge length is the average length of one side of a tetrahedral zone. It will try its best to fill up the blocks with zones of that size. Certainly when you have zones that are not perfect cubes like this, you can get some that are smaller and some that are bigger. The reason we use tetrahedral zones in 3DEC is because it's easy to fill up, well, relatively easy to fill up any volume with tetrahedral zones. In fact, you can prove mathematically that you can fill up any volume with tetrahedral zones. That is certainly not the case with hexahedral zones that Fleck 3D uses. Because the geometries in 3DEC are often very weird and ugly because people cut a whole bunch of joints in there, it's almost always easier just to fill up the space with tetrahedral zones. We recognize that tetrahedral zones are not as accurate as the hexahedral zones. However, we're assuming that in 3DEC, you are more interested in the behavior of the joints and the structurally controlled deformation than you are in the failure of the material. Obviously, the material will still fail. You will still get plasticity. You will still get deformation in the material and so on. It will not be as accurate as it would be if you used hexahedral zones. That is a concession that we will have to live with in order to be able to fill up these shapes in a reasonably efficient way. Okay, so block zone generate edge length 1. We can just run this. You can look at the zones. So if I run this, press the green arrow, go up to my blue arrow and go to new and make a plot. And let's just call it block. As in the previous tutorial, we go to the plus and we add a block. The difference now is that you will see how this block is full of zones. These are tetrahedral zones. You can see this triangulation on the surface. There's some number of zones inside of this thing. If you really want to know how many zones are in it, you can type a command. So remember, interactively, you can type commands down here in the console. And one of the that is sometimes useful is block list max. And this will just give you some statistics about what's in your model. So the number of blocks is 1. The number of vertices, 1,331. The number of zones, 6,050. Gives you information about the mass and the volume. It also gives you information about contacts. In this case, we don't have any. Sometimes it's useful to know how many zones you've created before you start running a model that might be really slow. Okay, notice that popped up in its own new window here. I can go back and click on console to see what's happening as I execute these commands. Okay, recall in the previous example, the blocks were rigid, so we had to fix entire block if we wanted things to not move. Now they are deformable. We can fix this grid point by grid point. So we can fix all of the grid points on the bottom and fix all of the grid points on the back with a command like this: block grid point apply velocity, and I can give the velocity x, y, and z components of velocity that I want to apply to those faces. 99% of the time, you're just using 0. You're just fixing it, okay? We use velocity in 3DEC because it's an explicit program, and it uses velocities for everything. Obviously, if you specify a 0 velocity, it's the same as specifying a 0 displacement. We're essentially fixing it so they can't move. We just use velocity instead of displacement because it's an explicit program. So I'm going to fix the grid point velocities in all 3 directions on the bottom. So I say range, pause Z. And I'm also going to fix the velocity of all 3 components on the back. So I'm assuming there's some rock material to the right, and there's some rock material below, which I'm not going to model, but instead I'm just going to fix the boundary. So block grid point, apply. Again, I can be lazy here and I don't have to type the whole thing. I can just say vel 0, 0, 0, range, pause, x, 10. So let's put the axes on here so you can see what I'm talking about. Okay, so I fixed the bottom. I fixed the right-hand side. I'm assuming that this extends a long distance into the plane and out of the plane. So I can assume that it's basically symmetric in the y direction. And the way to simulate a symmetry is to fix the displacement, but not in all three directions, just in the perpendicular direction. So I can do this: block, grid point, apply, vel y 0. So I'm only fixing the y component of velocity. It's free to move up and down, and it's free to move it side to side. And I say range, pause, y 0. I can just copy and paste that. Choose pause y 10. And I can even leave myself a comment here. Symmetry conditions on the front and back. Okay, so I've made a block, I've zoned it, I've got the boundary conditions. Now the fun part where we do the constitutive model and the property. So again, often you would want to run this. If it was a more complicated model, you would want to run it elastically first to make sure everything was okay. This one is so simple that I'm going to skip that step and go straight to Mohr-Coulomb. So block, zone, C model, which stands for constitutive model, but you don't want to type out constitutive model, it's a lot. So block, zone, C model, assign Mohr-Coulomb. Okay. This will turn everything into Mohr-Coulomb material. Once I have assigned a constitutive model to all the zones, I can give them properties. And again, I can't give the properties before the constitutive model because who knows what the properties are, right? So block, zone, property. Density. In 3DEC, you always have to give a density. And again, I'm going to assume that we're using meters and pascals. So density is kilograms per meter cubed. We give a Young's modulus, which will be in Pascal. So let's pretend it's a 1 gigapascal Young's modulus. I give a Poisson's ratio of, let's say, 0.25. So these are elastic properties. If I was just running this elastically, these properties would be enough. That would be fine. For a Mohr-Coulomb material, I usually specify a cohesion and a friction and a tension. So let's just say for now, friction 40. That's in degrees. Now I'm going to make another line to sign the cohesion and the tension because we'll run this twice. We'll run it with one cohesion and tension and it will be stable. And we'll reduce the cohesion and the tension and watch it fail. So I'll just put this on another line to make it easy. Block, you can obviously make as many lines as you like. Block, zone, prop. Again, I don't have to type it all out if I'm feeling lazy. Block, zone, prop. Cohesion, 25. Tension, 24. Again, this is pascals. I turn on the gravity model. Gravity 10. Remember, if I don't give the full vector, it assumes that I mean that gravity is acting downwards in the z direction. So 10 meters per second squared downwards in the z direction. I'm going to record a history of displacement at a point on the top. So we've seen this before, block history. In the previous example, we recorded velocity. Here we can record displacement in the z direction. Give a position 0, 0, 10. So this is the top front right corner. Okay, that's everything. Now we've got boundary conditions, we've got properties. One more thing we need to do is tell it whether we want large strain or small strain. In this particular case, Small strain is fine. Large strain is often useful if you have things moving a long way and you have new contacts forming or contacts disappearing and things like that. In this case, there are no contacts. If it fails, it's a disaster. If it doesn't fail, it's not moved very much. So small strain is fine. It will run slightly faster in small strain because it does not need to update the coordinates. Okay, now here is some new thing for you. So in the past, in the previous example, you saw we just use model solve. It will run until the ratio of unbalanced force to applied force is less than 1e minus 5. That's what we'll do by default. In this particular example, we actually don't know if that will ever happen. We don't know if this is stable or not, if it will actually reach that solved stable state. So what we can do is put like a fail-safe in here to make sure that it doesn't run forever. Okay. So by default, the solve criteria is ratio 1e minus 5. So if I just type this, it will do exactly what happened before. We'll use that default to determine whether or not it's at the steady state. But I can add another criteria, and I can say, or cycle 2000. So what this is going to do, it's going to try and solve and get to that ratio of 1e minus 5. But if it does not get there within 2000 cycles, it will stop. So there's two different criteria here. It's checking the unbalanced force ratio. It's also checking the number of cycles. If either one of those is met, it will stop. And this is useful to do when you don't know whether or not something is going to be stable. One last thing in this command we can add is a keyword elastic. Model solve elastic ratio 1e minus 5 or cycle 2000. What this keyword does is it turns everything to be elastic, solves it, then turns everything to give its true strength and solves it again. You know, if everything is elastic, it will solve. It will definitely reach that ratio at some point. Nothing fails, it will solve, right? It is useful in a situation like this. So note here that we did not specify any initial stresses. So this thing is unstressed. We're turning on gravity. What you're going to see is a huge downward force acting on all the grid points because of this gravity. This instantaneous huge downward force can actually cause things to fail right off the top. It's essentially setting up a dynamic wave that propagates through the system with a fairly high amplitude. That's not realistic. Gravity doesn't just turn itself on magically. So we kind of don't care about the state during this initial equilibrium, due to gravity. So what we can do as kind of a shortcut here is we can say, all right, make everything elastic, solve. We know that things are going to move and there's going to be waves bouncing around, but at least it will not cause failure. Once it's come to some steady state, turn it back to the true strength, keep running, and see what happens. Okay, so this is just a useful shortcut to sort of get to the initial state without causing failure, and then seeing what failure occurs due to the stresses there. Okay, that's it. So let's run it. You press the little green button here. It generates the zones, and I missed something. Plot grid point, apply velocity 0, 0, 0. Oh, I forgot to give a position for the boundary. Range, position, z, 0. That's the bottom. Note that with these ranges, you can either give a single number, which means that it will just find all the grid points that have a position of 0. Within some tolerance, there's a default tolerance. I think it's like 1e minus 5. So any grid point that's sitting at 0 will get fixed. You can also give two numbers, and then it will find all the grid points between 0 and 10 or 0 and 5 or whatever. But if I just give one number, it will just find all the grid points sitting exactly at that position, more or less, within some tolerance. All right, let's try this again. I run it, generates the zones. Okay, it's quite quick. This is a relatively small model. I'm just going to expand this console pane a little bit so you can see what happened. It ran 1,000 steps. It reached the mechanical ratio, 20 minus 5. And then it started running again. It ran another 808 steps. So again, this is because we used that elastic keyword. It turned everything elastic. It ran. It turned everything to be a true strength, and it kept on running. You can see this better if we plot a graph of the history. So let's make a new plot here. We go up to new plot, call it history. Go to the plus, go to charts and choose history chart. We hit the plus over here under attributes to add the one history that we defined, the z displacement. So you can see what's happening here. There's initial downward movement because, again, we turn on that gravity and there's a big downward push. It bounces around a little bit, comes to some equilibrium. This is everything elastic. Then it turns everything to its true strength, and you get some more downward movement. So presumably something in here failed. If nothing failed, nothing would happen. Some zone somewhere failed. There was some stress redistribution. We end up with a little bit more displacement than we had to start with. Let's go have a look at the model. So if you click on the block, here's just the block. We can check to see if something failed in here. So if I click on, in the plot item list, I click on block ID. Here are the attributes. Color by label, so that means that every zone gets its own color. By default, it labels to the ID of the block. In this case, there's only one block, so the ID is 1. I can change that to state. And now we get change in color based on the plastic state of the material. So the blue zones are none, they've never failed. The green zones are tension-P, which is short for tension in the past. So it means that these guys failed in tension at some point during the simulation. But what happened is stresses get redistributed and they get unloaded and they go back to being elastic again. So they failed in tension at some point in the past, but everything redistributed itself and everything came back to equilibrium and everybody's happy. There's nothing failing now. If this said tension-N, things would still be failing. Here, nothing is failing. We can assume that it reached this equilibrium. Again, you can see that it ran 808 steps. It did not reach that 2,000. It did reach that mechanical ratio limit. So we can assume that this is at a steady state. Further evidence of that by looking at the history. Again, it's pretty flat at the end, indicating that things are not moving. As well as the state here, we can look at, for example, the displacements. So if I change this label to contour, by default, it shows me displacements. There are other things I can contour. For now, we're looking at displacement. So this makes sense. Remember, we fixed the back and we fixed the bottom. We're getting displacement that looks like this. If you want to know more about the direction, we can go to the plus and add vectors. You can see the direction of movement of this displacement. And this is pretty much what we would expect. Some movement down and to the left here, but not a lot. Maximum displacement, 1.5 millimeters. This is a pretty stiff material. Remember, it was 1 gigapascal Young's modulus. There's not much failing. We're not seeing a huge amount of displacement here. This gets more interesting if we make it weaker. So if we go back to the data file, in this line 18, block zone property cohesion, 25 tension E4, let's make it 10 times weaker than that. Let's make it cohesion 1E4, tension 1E3. Let's run that. Everything else is the same. So it ran the first part elastically, it solved, but now look, it did not reach this mechanical ratio of 1E minus 5. It did reach 2,000 steps. It stopped running. We can go look at the block. Now we're seeing fairly significant displacements here. This is 37 centimeters. If we go over here to the attributes and we change this, sorry. Sorry, that's the vectors. If I click on block displacement magnitude in the plot item list, I change the color by back to label. The label goes back to state. I can see all kinds of failure here. So these light blue ones haven't failed. Everything else has failed at some point, either shearing now, or sheared in the past, or tension now, or tension in the past, or some combination of those things. So you get all these complicated colors here. Maybe we don't care about the things that failed in the past. We only care about the things that are failing now. There's actually a checkbox over here. If you look under the attributes, there's a checkbox for no past. The ones that just failed in the past, we'll turn them back to light blue. So maybe these guys failed in the past and stress was redistributed. But all of these guys are failing now, either in tension, in shear, or a combination of tension and shear. And so this whole section of block here is actually failing fairly catastrophically. You can see that in the history here as well. There's a little blip in history. This was this few millimeters that we saw before, but now this thing starts failing and it just keeps on going and it's a catastrophe. So that's the end of this example. That was just a simple example to show you how to zone something and assign a constitutive material and assign properties and look at the states and displacements and so on. So I hope you enjoyed this session and more will follow.